the screen. How about now?
No, I can't. Yeah, so yeah, now okay, fine.
Now okay, right?
Yeah,
Yeah, I mean the
You
nuances.
may press you may press the hide so that
yeah,
that thing goes off.
Thank you. You're right. I find that annoying myself. The hide in the bottom left, bottom center of the screen. So, Professor Pradeep, thank you very much for continuing this initiative for what I understand for several years now. And Subrata, personal thanks to you for making sure that everything was on schedule and all the links worked out.
yeah.
So when
I'm
initially I
also
got
glad
got
that
this,
ultimately we have assembled together time, dates, and this time that Google Meet and what it's called that Zoom link. It will not work and all those stuff. But welcoming. Please go ahead.
it would have worked because what I did is because today there were predictions of thunderstorms.
Yeah.
I came back home early, so I could have just used Zoom. But
Okay.
I didn't know when you invited me that there
Okay,
will be
fine, fine.
thunderstorms.
Yeah, yeah. Okay, please go ahead.
So when I got this invite from you and Professor Pradeep's group, I thought I was going to make a new lecture because I hold Professor Pradeep in very high regard. I mean,
Yeah.
he's literally a very unique scientist in the whole country, and if there was just one other person like him, you would have seen a very different scientific scenario in India. And I've interacted with him for in different platforms, and particularly in funding agency, the proposal evaluation committees, and I cannot tell you how much this person means to the young scientists in the country, and I'm a beneficiary of his generosity and support. So, but then the point is, I wanted to make a new lecture, and I wanted it to be about something that we are now getting into, as to how hydrogen bonded water in catalytic sites are not like bulk water. And two of my students who are in this meeting who has joined, I just saw them. They know what I'm talking about, and that's something we have just started exploring. How, if you have a hydrogen bonded water which is catalytically active, that water is very different from bulk water. I wanted to talk to you about that, but some of 2D IR experimental data that I was hoping will come through did not come through. So I decided, okay, let's talk about how we can use water to reduce CO2, because that's something that Suman in my lab he started doing. He's not an IIT Chennai alumni; he's IIT Guwahati alumni. The IIT Chennai alumni in my lab is Somya Samanta, and he's been working on oxygen. So what I'm going to talk about today is about CO2 reduction. Now, when you look at the literature and if you look at it superficially, and you see the work being done on CO2 reduction, you would see most of the papers coming out on how it produces carbon monoxide. Very few paper on anything beyond that. Maybe you will find now and then a paper on methanol, which is like 6% methanol. The rest is carbon monoxide. Maybe there's some methane, 5% methane. The rest is carbon monoxide. So what we have been able to do with the help of the investigation that Suman, who is in the audience, has done, is we have been successful in breaking this barrier of CO2 reduction beyond 2 electrons. Now, what do I mean by that? Well, carbon dioxide has carbon in a formal oxidation state of plus 4. In methane, carbon oxidation state is minus 4 formally. Okay, so essentially from carbon dioxide to methane, you can deliver 8 electrons. If you deliver 2 electrons to carbon dioxide and 2 protons, you can either get carbon monoxide or you can get formic acid. Let me turn on the pointer. So either you can get formic acid or carbon monoxide with 2 electrons. You add 4 electrons to carbon dioxide, you get formaldehyde. You add 6 electrons, you get methanol. You add 8 electrons, you get methane. Now, when you think of why we are reducing carbon dioxide, an argument that comes on now and then, apart from the big issue of CO2 being a major contributor to global warming, I'm not addressing that. I'm addressing CO2 as a source of valuable chemicals. When you look at the list of chemicals in this slide, formic acid, carbon monoxide, formaldehyde, methanol, methane, they're all useful. Formaldehyde and methanol particularly are very useful because you use them as starting material of polymers. Okay, carbon monoxide you use for polymerization in Fischer-Tropsch. Methane is essentially what you get from biogas, fermentation of from cows and pigs, ruminants, and that can work as a fuel. The problem really is if you look at the thermodynamic potential for all these processes, the two electron processes, formic acid and carbon monoxide, are most thermodynamically demanding. These are potentials versus hydrogen electrode at pH 7. Everything else, 4 electrons, 6 electrons, 8 electrons, they are actually less thermodynamically demanding. Yet, when you reduce CO2 and you look across literature, most of the products are limited to carbon monoxide. And there are some reports of methanol and methane, but then these are all mixtures. You don't get them pure, okay, except CO. You do not get pure methanol, you never get pure formaldehyde, pure methanol. I mean, pure formaldehyde would be lovely because formaldehyde, paraformaldehyde is a starting material for polymer that you can use, but there is no such report whatsoever. And all of these are in the same thermodynamic potential. So once you give enough energy to reduce CO2 by 2 electrons, 4, 6, 8 becomes easier. Okay? Apart from that, if we try to reduce CO2 to carbon monoxide, formic acid, whatever, you're going to need protons. Okay, that's the H in formic acid or formaldehyde. Now, this proton can also be reduced to hydrogen at a potential which is very similar or even lower than 2 electron reduction potential. And herein lies the biggest problem in getting CO2 reduction to work: selectivity. How do you get one product out of hydrogen, carbon monoxide, formaldehyde, formic acid, methanol, and methane? And that is something we have been investigating for the last, I would say, 10 years now. What determines, or as a chemist, how do I approach selectivity in this reaction? Okay. When you think of CO2 reduction, it's a matter of adding electrons and protons. How difficult can it be? But when you look at the energetics, you actually have a lot of options in terms of the products that can be formed. And therein lies the challenge in CO2 reduction. Now, back in, I would say, 2020, we solved one of the major issues on CO2 reduction, and that was pertaining to the factor that controls selectivity of 2 electron reduction. If you reduce CO2 by 2 electrons, 2 protons, you get formic acid or CO. Now, how do you make only CO? How do you make only formic acid? Now, don't get me wrong, there were reports of pure CO in the past. There were some reports of pure formic acid in the past. But there was no clarity as to how you can control that. And we sort of figured out, this is Manula, he is now a faculty in Marseille in France. What he, in combination with Biswajit, who is now in IIT Gandhinagar, they could show is when CO2 binds iron porphyrins, it makes this intermediate iron 2 CO2 2 minus. This was Biswajit. This can only be observed at minus 95 degrees Celsius in a very weakly protic solvent like methanol. Okay, you warm it up to minus 80, it forms an intermediate which is iron 2 COH. Now, this iron 2 COH intermediate was the branching point for formic acid and CO. This iron 2 COH intermediate can be protonated either in carbon. If you protonate this carbon, what do you get? You get formic acid. Or in the oxygen. If you protonate this oxygen, this CO bond cleaves, what you have left is carbon monoxide. So that was the first realization we had, that the selectivity between carbon monoxide and formic acid was determined by the site of protonation of this metal COOH species. And that can be controlled by controlling the electronic structure of the species. What do you mean by that? Well, whether the carbon will be protonated or the oxygen will be protonated depends on the negative charge on the carbon or the oxygen. The metal can be high oxidation state, low oxidation state. It can be high spin, low spin. Now, go back to your basic inorganic chemistry ligand field theory. A metal that is low spin forms very strong metal ligand bond. So that's very strong covalent interaction. When that happens at a high oxidation state, then this carbon center is depleted of all the negative charge. And the negative charge resides in this oxygen, resulting in oxygen protonation, cleavage of the CO bond, and release of carbon monoxide. However, if the system is low oxidation state or high spin, then there is negative charge on the carbon, which then gets protonated and you get formic acid. So, high oxidation state, low spin, carbon monoxide, low oxidation state, high spin, formic acid. Now, this is something we realized a long time back, and we actually have an accounts article on this in 2022. You can check it out. So, we sorted this out a while ago, that whether it's carbon monoxide or formic acid depends on where you deliver the proton, the carbon center or the oxygen center. Okay, we got that. Okay, everything fits in so far. Now, we want to reduce carbon dioxide predictively beyond 2 electrons, that is beyond carbon monoxide and formic acid, to make formaldehyde, methanol, methane. Now, what is known? Well, you take a reduced metal, you bound CO2, you get this CO2 minus intermediate. This is something Biswajit Mandal, who is now in IIT Gandhinagar, showed. You bind a proton to this. This is very basic, 2 minus ligand. Bind a proton to this, you get the COH intermediate, which carbon protonation gives formic acid, which oxygen protonation gives CO. That's good. Alternatively, you can actually protonate the low valent metal center with a proton and get a metal hydride intermediate. This metal hydride intermediate can attack a CO2 and make a formate. Now, this is something Jenny Yang in Irvine, her PhD advisor, Kubiak in San Diego, they have shown a long time back that you can make formic acid from metal hydride intermediate. We are not interested in that. We want to actually harness the power of this common intermediate and then control the branching between formic acid and carbon monoxide. Now, where is the problem in trying to reduce this further? So what is known is when you try to reduce, let's say, this metal carbonyl further with the goal of reducing this carbon center in its plus 2 oxidation state, this carbon monoxide comes off. And that is why you cannot reduce CO2 beyond carbon monoxide. Okay? Now what Mark Robert he's now in Sorbonne, he was in University of Paris Diderot before this, he's moved to Sorbonne now, him and Bing Lu with his theory showed that in principle if you can stabilize iron carbonyl intermediate, you should be able to reduce this further. And they had some systems where they saw some methanol, okay? Now this is not new. Wolzansky, who was in Cornell, just retired, and Barkhaw, who was in Caltech, when Wolzansky did his PhD with Barkhaw back in the early 80s, they actually showed that you can take a zirconium complex, bind CO2, and then make a carbonyl, and as long as the carbonyl stayed bound to the zirconium complex, you could transfer protons and hydride to the carbonyl and make methanol. So for us, the problem was how to make the carbonyl stick, okay? Well, there's something that's very common in our lab is hydrogen bonding. We have actually paid a lot of attention to how hydrogen bonding to these intermediates can change the course of a reaction. We started with oxygen reduction, and we have now explored nitrite reduction, SO2 reduction, CO2 reduction, and we have always found that hydrogen bonding can stabilize reactive intermediate, allowing further reactions. And let me show you how that worked in CO2 reduction. So this is a system Escamanula, who is now in Marseille, he developed. This is an iron chlorine species. Why chlorine? Because if you pay attention to this pedal ring, 2 of these carbon centers are saturated, okay? And what he did is he installed this nitrogen, which is very close to this carbon center. Now this iron chlorine system would reduce CO2 with very low overpotential all the way to formic acid. This was a sharp contrast to CO2 reduction by iron porphyrins, where the rings are not saturated. Anyway, you know why that is, because CO requires oxygen protonation, formic acid requires carbon protonation. So what the system did, in its iron 1 state, it would bind CO2 and proton at the same time, and the proton would go through this nitrogen, which is basic, and make this iron 3 COH intermediate, which we trapped, synthesized, characterized with Mossbauer, Raman, IR, all kinds of spectroscopy. This, under applied potential, which was minus 1.5 volts approximately against ferrocene ferrocenium, would get reduced to a iron 2 COH intermediate, which then gets protonated at the carbon, releasing formic acid, generating back iron 2 chloride system. But if you look at the electrocatalytic response, normally if you look at the cyclic voltammetry, is the iron 3-2 process, 2-1 process, 1-0 process, and this is a ligand reduction. The CO2 reduction in the presence of CO2 and water happens at iron 2-1 process right over here. But beyond that, there is a small process corresponding to this iron 1-0 state. We thought, okay, let's look at what's happening there. So what we did is we applied a potential corresponding to the iron 0 state in the presence of CO2 and water as a proton source, and then we analyzed the mixture. What we saw is as we change the water content of the medium, the product changes. So if we have around 100 millimolar water, we get a lot of formic acid. If we increase the concentration of water to 1 molar, formic acid really goes down from blue to orange. So this system is not making formic acid anymore when we increase the water. Okay, this is going to become very important. So we analyze the mixture, and what we see is methanol. Methanol goes up from 0 in 100 millimolar water, where it's all formic acid, and then you can slowly see methanol form and maximize at around 2 millimolar water. And here's the yield of formate, methanol, formaldehyde with water concentration. At low water concentration, it's all formate, no methanol, no formaldehyde. As we increase the water concentration, formate goes down, methanol goes up till 2 millimolar, 2 molar, when methanol is 48%. Now, what does this mean? This means that now a system that was making previously 98% formic acid can make 50% methanol. As a fuel, methanol has a few advantages. One, it's a liquid that can be stored, stable, and transported in vehicles. Two, it is also a feedstock for polymerization industry. So when we saw this methanol, 48% from CO2, we were pretty excited, okay? But then, let me warn you. I already warned you at the beginning of the lecture. We love mechanism. We wanted to know how a system that was producing all formic acid at very little water concentration now produces methanol when you increase the water concentration. What is going on here? Okay, so first you have to make sure that the methanol comes from CO2. You do that by using isotopically level CO2, and we did that. We know the methanol comes from CO2, it's all good. Now, this is what we're going to do for mechanistic investigation. We're going to do spectroelectrochemistry FTIR in situ while the system is doing its reaction. Then we're going to chemically prepare the species and compare the spectroscopies of these and come up with a mechanism. So when we do in situ FTIR, that is when the system is doing CO2 reduction, we monitor the FTIR, we see it forms an iron 2 COH species, then an iron 1 COH species, we think, and an iron 1 CHO species. Okay? How do you know these are iron 2 COH, iron 1 COH? Let me tell you that. First, you isotopically substitute the CO. If this COH species, this vibration, okay, at 1682, if it comes from CO2, if you substitute the CO2 with 13 CO2, the vibration is going to shift. Okay, the same applies to all of these. And this is what we get. 1682 with 13 CO2 goes to 1638, 1662 of this formula goes to 1618, 1641 of what we think is iron 1 COH goes to 1599. So these are indeed originating from iron COH atoms. Now, the key conclusion for this, because we have characterized the iron 2 COH before, for us was this iron 2 COH, you go to a lower potential, makes iron 1 COH, which gives methanol. Okay, so let's confirm the iron 1 COH. Spectroscopically, under electrochemical conditions, we saw iron 2 COH at 1682 get reduced to 1640. We thought it was iron 1 COH. We wanted to confirm this. So we took this complex, reacted with CO2, make iron 3 COH. We have done this in the past. Reduce it to iron 2 COH. We have done this in the past. Now apply a strong reducing agent, similar to the potential we're applying during spectroelectrochemistry. Reduce iron 2 COH by 1 electron. When we do that, the species that we get chemically also has the same spectroscopic features, FTIR, as the one that we see under spectroelectrochemistry conditions. So adding 1 electron to iron 2 COH does actually result in a species that we see in spectroelectrochemistry. We think it's iron 1 COH. How do we confirm that? EPR. When we look at the EPR spectrum of this iron 1 COH species, we see G values which are here, 2.35, 2.21, 1.96. It's a D7 low spin iron system. Okay, if the system was, let's say, D6 and the porphyrin ligand is reduced, 1 electron on the ligand, then the signal would have been similar to a radical signal with G equals to 2. Anytime you see a G more than 2.05, it's a metal-based spin, because the only way you deviate from G value of 2 is using spin-orbit coupling, which is much higher in metals than in ligands. So this is a low spin D7 system, which is iron 1. So the intermediate that's forming in the pathway to make methanol is iron 1 COH. Okay, we also use a bunch of Raman techniques to confirm this. So here's the mechanism. This iron 2 COH species gets reduced to iron 1 COH species, which we see under spectroelectrochemistry as well as chemically prepare this. This iron 1 COH has two options. Either the carbon gets protonated or the oxygen gets protonated. Now, of course, from our experience with iron 2 species of the same ligand, the carbon protonation is lower in energy. It's high spin. Okay, this one was high spin. So we thought the carbon protonation is lower in energy. And in fact, it is. Because when you have low concentration of water in the medium, what you get is all formic acid. So at low concentration of water, you get carbon protonation, you get formic acid. However, when you increase water concentration in a solution saturated with CO2, you make a lot of carbonic acid, so the acidity goes up. And when the acidity goes up, you start protonating this oxygen. And when you protonate this oxygen, you cleave the CO bond, you form an iron 1 CO species. Unlike other iron 1 CO species that dissociate, this iron 1 CO species is stabilized by hydrogen bonding from this NH. So it doesn't go off, allowing its further reduction to release of methanol. So the key here is carbon protonation at low acid strength and partial oxygen protonation at high acid strength giving to methanol. Why do I say partial? Because since the carbon protonation is thermodynamically more favorable, no matter what acid you use, the carbon would always be preferentially protonated. The maximum thermodynamically uphill oxygen protonation you can get is 50% if you use a strong acid. And that's exactly what we are seeing. 48% methanol from oxygen protonation. Okay, so we learned this thing, that if you can stabilize this iron 1 CO species with hydrogen bonding, it seems like you can reduce carbon monoxide further to get more reduced species, which is what we want to do to begin with. Let's explore this idea a little bit, shall we? So here's the problem. Porphyrins, you get reduced, you make CO, formic acid, whatever. Once this CO is reduced to iron 1 CO, the CO comes off. We should be able to stabilize this iron 1 CO from hydrogen bonding. That's the idea from the last study. Now this is where Schumann comes in. And what he did is he took this iron porphyrin with this pendant pyridine. Okay, we had seen an oxygen reduction. This pendant pyridine through a water, hydrogen bonds to whatever is there bound to the iron. So he used this pendant pyridine containing iron porphyrin to reduce CO2. Well, normally this would reduce CO2. All iron porphyrins do nothing very special. Selectively CO, it's all good, no problem. However, when he took carbon monoxide, which is never reduced by iron porphyrin, he sees this in green, a nice CO2 reduction wave, CO reduction wave, carbon monoxide reduction. So this iron porphyrin, unlike all reported iron porphyrins in the past, can reduce carbon monoxide. Okay, what's the product? What Suman identified that the product was pure methane. Okay, remember, CO is 2 electron reduced, methane is 8 electron reduced. From 2 electrons all the way to 8 electrons just by introducing one pyridine group in iron porphyrin. Of course, we want to know, we're mechanism people, what the hell is going on, okay? So first we confirm the methane comes from CO2. We do that with isotopically leveled CO2. We do that with replacing protons with deuterium, analyze the product, make sure it's all good. It's all from CO2, okay? However, the Faraday yield, which is how much electrons actually go to make methane, how much goes to make CO, how much goes to make hydrogen, the ratio, that for methane was very low, okay? Only 6.3%. Not much, but we got methane. And we wanted to use that to understand how are we getting methane. Clearly, we are getting methane from reduction of CO2 beyond carbon monoxide. So we decided to look at carbon monoxide reduction by the iron porphyrin in slightly more details. We did in situ FTIR. We identified with applied potential what are the iron carbonyl species that were forming. Iron 2 CO gets reduced to iron 1 CO, which gets reduced to iron 0 CO, and which gets protonated to make iron 0 forming, iron 2 forming. We corroborate these experimental frequencies with DFT calculations. In DFT calculations, we had the COs. You see, this is iron 2, iron 1, iron 0, but no hydrogen bonding, just this dangling pyridine, okay? Then we introduce water to a hydrogen bond between the pyridine and the CO. If you look at the frequencies, for iron 2 CO, not much difference with hydrogen bonding. But for iron 1 CO, there's a huge difference in the CO stretching frequency when you introduce hydrogen bonding. It goes from 1948 to 1934. Okay? Now that's a big change. The experimental iron 1 CO that we were seeing was 1935, which is very close to 1934. So we thought we are going to use this particular iron 1 CO adduct to confirm the presence of hydrogen bonding. So we made iron 1 CO in very dry solvents. Okay? And here's the CO stretch, 1951. See, 1948, very close. We made iron 1 CO in solvent with 3% water, 1935. That's very close to 1934. So actually, the water hydrogen bonding with the CO reduces the CO frequency from 1951 to 1935. And that's because the hydrogen bonding stabilizes the back bonding from iron 1 to CO pi star, which makes the CO negatively charged. And you have a water stabilizing that negative charge. So water facilitates back bonding from iron to CO, stabilizing the iron CO adduct. Okay? But still, how much is this stabilization? So Shuman did this estimate of the CO off rate using cyclic photometry, and he saw that there's almost 3 orders of magnitude reduction in CO dissociation from the iron 1 state without and with hydrogen bonding. Now that's quite a lot. Okay? Still, when you reduce CO2, you're getting only 7% methane. The rest of the carbon dioxide is forming CO. So which means when you're doing this chemistry in solution, you have an electrode, right, with the electrons. You have your catalyst swimming around in the solution, protons swimming around, CO2 swimming around, and the catalyst comes to electrode, gets reduced, forms this intermediate, swims around a little bit, comes back, gets reduced, and does this. So the kinetics is diffusion limited. So what that means is once you make the iron 1 CO, it goes off from the electrode because this is an organic solvent solution. It has enough time to dissociate before it can be reduced. So what someone did, he took the iron porphyrin and he heterogenized on an electrode, which means chipak diya. He attached the catalyst onto the electrode so that this electron transfer is fast. And when he did that, the GC shows we can actually reduce CO2 all the way to methane. Previously, when we were doing inorganic solvents with CO2, this was the CO peak in GCMS, this was methane. When we heterogenize in water now, CO, methane, it's all methane. More than 90% selectivity for methane, or 8 electron, 8 proton reduced of CO2 by the same catalyst when heterogenized. Okay, so we can make like around 150 microliters within 1 hour or something. All right, now what did we learn? We learned previously that the selectivity between formic acid and CO is determined by the spin state of this iron COH intermediate. The low spin state forms this iron CO intermediate, which then goes oxygen protonation, makes CO. This CO, when reduced by 1 electron at the electrode, makes iron 1 CO, generally goes off, giving you CO as the product. However, when you stabilize this iron 1 CO by hydrogen bonding, it can be further reduced to iron 0 CO and iron 2 formyl species. In the high spin domain, you have this iron 2 COH with very loosely covalent iron carbon bond. This can be protonated at the carbon to give you formic acid. Okay, we have this selective formic acid from high spin iron system. Now, if you can stabilize this formic acid, you can reduce it to iron 1 CO. Here too, you can protonate the carbon at the oxygen. Protonation of the carbon is energetically more stable and you get formic acid. However, if you use a stronger acid source, you can protonate the oxygen and you can make this CO, which is then stabilized by the iron hydrogen bonding, and you make a formyl intermediate. Okay. Now, in the low spin formyl intermediate, analogous to this iron 2 COH intermediate, this carbon is difficult to protonate. However, in this high spin system, this can be protonated, which is why we got around 17% formaldehyde from the system. Okay, but once you reach the formyl intermediate, both high spin, low spin, what happens next? If it is stable enough due to hydrogen bonding, you can reduce this further. The low spin formyl, you can reduce further all the way to methane. And drawing analogy with what Ertl had figured out on copper surfaces, it probably goes through a series of carbene and iron methyl intermediate to give you methane. Now, we have absolutely no proof of any of these speculations, okay? Similarly, the high spin formyl can be reduced to something that eventually gives methanol by carbon protonation. So, carbon protonation gives you formic acid. Carbon protonation of this formyl intermediate gives you formaldehyde. Carbon protonation of this methyl alcohol intermediate gives you methanol. All these partially reduced species are coming from carbon protonation. Low spin, only oxygen protonation, you get CO or methane, nothing else. Nothing else comes off because everything is held so tightly. Okay? Now, with this, we thought, okay, can we do something else? Because what we are saying is for the low spin system, which gives methane, we are going through carbenes. Now, carbenes, if you ask an organic chemistry, they're going to jump with joints. Yoo-hoo, carbenes, because carbenes are very reactive carbon 1 sources. Now, can we do that? Okay, there's precedence in literature. So, for example, if you look at methionine synthase, an enzyme that converts homocysteine to methionine, there's a thiol group which forms a CS bond with a cobalt methyl species. Now, here we are proposing an iron methyl species. Can this form a CS bond? To explore that, we made a series of iron porphyrins with this pendant thiol groups. This is Shovik Dinda, he's the PhD student, very good synthetic chemist. He made the complexes, and Shuman and Shomili, they did the experimental chemistry. So we made these, and then we looked at CO2 reduction. Okay, what happens? Well, With thiols loosely attached to this iron porphyrin, we get ethane, C2H6. Now, ethane is a primary component of natural gas. That's what cows and other organisms that chew grass, they emanate from their digestive system. We were so shocked for a long time. I did not believe we were getting ethane. Okay, so I had Shuman do a bunch of control experiments to make sure that what he was seeing is actually ethane. Now here's the GC graph, and here you can see we're increasing the water concentration in the medium, which is acetonitrile. Initially at low water concentration, there is just carbon monoxide. As you increase the water concentration a little bit, you see this peak for methane come up. If you increase the water concentration a lot, you start seeing hydrogen. If you plot the relative population of carbon monoxide in green, purple, ethane in green, and hydrogen in orange, at around 1.5 molar water or 2 molar in that region, we are making around 40+% of ethane from CO2. And again, of course, we know it's coming from CO2 because when we isotopically label the CO2, we get isotopically labeled ethane. Okay. The question is, how on earth we are getting CO2 from ethane from CO2? Because previously we were getting C1 products, which makes sense, right? Even iron porphyrin captures the CO2, keeps on pumping protons and electrons. Yeah, high spin, low spin notwithstanding, we get a single carbon product. But now we are forming CC bonds. How are we forming CC bonds? So what we when we looked back at known literature, what we figured out is iron porphyrin carbenes are known to be attacked by thiols. Now, this has been explored by Rudy Fazan and co-workers to make thioethers. So, what we think is going on is the CO2 gets reduced to this iron carbene, which was one of these proposed intermediates in our reaction, and the thiol group attacks the carbene, making a thioether. Okay, this frees the iron. When the iron is free, this can now reduce another molecule of CO2 and get you another iron methyl adduct or iron carbene adduct. Several possibilities. But what we think is going on, it's forming another methyl adduct, and then this methyl-methyl they're coupling. Okay. Now, if you look at organic chemistry literature and if you look at this David, what's this guy's name in Princeton? Not Milstein, David something. He does this CC coupling in organic chemistry with radical mechanism, okay? And what they're proposing is this comes off as methyl radical, which attacks this methyl group and it forms CC coupling. So we explored this, and what we found is you can make iron 2-methyl species. This is something Savyant has shown a long time back. He's now expired. He used to be a professor in University of Paris, did it all. So he showed that this methyl is a very good nucleophile. It can attack methyl iodide to make ethane. So we tested that. What we did is we made this iron methyl chemically, and instead of a methyl thioether, we put a ethyl thioether. Okay, which means if there is CC coupling, like what Savyant proposed, then we're going to get propane. And that is exactly what Shuman saw. Shuman saw that instead of ethane, when he used this ethyl ether, he saw propane with all C isotope labeling and everything. That was great. Now, which we wanted to test this further. How about we use dimethyl sulfide? It's a very toxic gas. When we use dimethyl sulfide, this methyl ether actually displaces the methyl group from this thioether to make ethane. Now, if you know organic chemistry, you have to understand this is serious business, okay? Because what we are observing here is that this iron methyl species, which is being generated from CO2, is such a strong nucleophile, it is displacing a alkane group from a thioether, which is not particularly electrophilic. but it is doing that. It's doing an SN2 on a thioether bond, making an alkane. We are really excited about this, and Shuman is doing a bunch of these experiments now to use this chemistry and do it. And I think if he gave a lecture, he can now tell you instead of 40% ethane, we can now make 80% plus ethane from CO2, which is very exciting. So I hope in this lecture I could show you by investigating the mechanism of chemical reactions how we can tune them to sort of enhance and diversify the reactivity that they were initially showing. For example, iron porphyrins had been known to reduce carbon dioxide specifically to carbon monoxide. That's Jean-Michel Savant, 1980s, known. We looked into the mechanism between 2015-18. We figured out a way to make formic acid by harnessing the reactivity of the iron 2 COH intermediate, making it high spin, using an electron withdrawing porphyrin group, and then making formic acid. Then we realized, well, the problem of CO2 reduction beyond 2 electron was, well, not us. It was known, it's dissociation of the CO. So then we use hydrogen bonding to stabilize this iron 1 CO adduct, which would generally come off, to allow its further reduction all the way by 8 electrons to methane with very high Faraday yield now. And then by looking at the mechanism of ethane formation, looking at this iron carbene, iron methyl intermediate, we could harness those intermediates and take this reaction forward and make ethane in very high yields now, but that's not published, so I'm not talking about it. So that's the story I had for you guys for today evening. And I must thank my students who did this. Biswajit, Sumishta, they started the initial CO2 work. Aman and Paramita did the high spin work. Shuman and Shomali, they are leading the work that we're doing now. And these are the funding agencies. And I'll be very happy to answer any question that you may have.
Well, what a pleasure to hear this story. Beautifully, unfolding this story of several years with a mission. And I hope that this mission becomes useful for people in the years ahead. All that you have to do is just control some water concentration and get what you want. So that's so first thing is, even with this kind of selectivity that you are having, how far away are we from using this method?
Sorry, can you repeat that, Professor Pradeep? I couldn't hear you.
How far are we from using this methanol for real industrial utilization?
Absolutely. So what we are doing right now is we are actually collaborating with a German group who has large-scale electrolyzers. So the samples have been sent, and we are waiting for the results. So we'll see how this works out. The good thing is these catalysts, they're very stable. They don't decay. So we hope that we are going to have some good news from them regarding methanol production and methane production in large scale on ethane using our catalysts.
Well, if you start thinking about the mechanism in greater detail, now you have your carbon that is sitting on iron, and now there is this oxygen, there is this other OH that is sitting around. This whole thing can rotate, and this specific thing is because of the nitrogen that is sitting around and that specific hydrogen bonding. However,
very well observed.
This can rotate. So now, if you start thinking about that,
true. That's a very good observation, Professor Pradeep. So we did compute the different geometries and their energies using DFT, and the rotation has a substantial barrier. Breaking that bond with this positively charged NH plus, and this COOH minus species is actually negatively charged. So the hydrogen bonding energy is quite a bit. Now, if you can flip it, overall thermodynamics would not be very different. Okay, but the barrier of flipping, where you break that bond between a positive NH and a negative COH, that's very high.
So it is essentially staying there.
Yeah.
Now, I was thinking that if you have a control on temperature, now will this rotation be third of with what current geometry? Can it be changed?
That's a very interesting idea. We have not explored that, but my students in the audience should take notes.
Okay. So the other thought that was there was that, well, you have water and its hydrogen bonded structures. And now, of course, there are many other hydrogen bonding molecules out there. Of course, one can investigate that. Is it possible? You talked about a few methane, ethane, propane, possibilities of this kind. But will this result in different other possibilities as well by controlling specific kind of structures, hydrogen bonded structures of that
So
transition state?
true, true. So as far as the number of products we can form from a single CO2 reduction, right now we have no clue as to how to get formaldehyde. We are getting it in some systems. Okay, so for example, here we are getting 16% formaldehyde, but we have no control. I don't know how to do that, because when you look at the mechanism, we need to attenuate the hydrogen bond to control protonation of this carbon center in its different forms. So if I want to make formaldehyde, for example, I need to protonate this formyl species, but not the COH species. And we don't know what the relative pKs are. And right now we are at least trying different hydrogen bonding group with different pKs and try to see if we can maximize formaldehyde, sort of like trial and error. But ideally, one should have idea about this. But in literature, there are not enough species, CHO species or COH species, which we can use or which are stable to determine pKs. So we are sort of shooting in the dark, in the sense we have an idea of what to do, but we don't have the exact numbers. This protonation energy difference between carbon and oxygen for this iron 1, we're the first ones to come up with this 3 kilocalorie barrier, right? Because we're the first ones to see these intermediates. So that's something we would like to explore in the future. We are doing it as we speak, but we'll see how that works out.
The other thing was that this carbene transfer is beautiful, fascinating. So what does it mean?
Right?
What does it mean? Does it mean that you can go and add a C1 to many systems? CH2s
Right?
are keeping added, and so
Yeah,
that
yeah.
means you can.
My student Suman is smiling right now, I'm sure, because he can tell you how many systems he can transfer a methyl group to.
Uh,
So
so
this is very
this is
interesting.
not, this is not, just a catalysis thing. You are actually doing organic chemistry in a different
Yeah,
way, right? So now then that comes to selective functionalization, right?
right,
So that
right.
where can you add? Where can you add? Where all you can add? Where all you cannot
See,
add?
one of the funny things, Professor Pradeep, is these porphyrins that we use, they already have some kind of static hindrance and structure to it,
Yeah,
right?
yeah,
So when you think about it, I mean, that's how organic chemists get selectivity.
yes.
So we are hopeful that this will be interesting. And Shuman is leaving. He's going to do his postdoc in a few months. Shomili, she's the young one in the group doing CO2. She's going to pick this up. We're pretty excited to see where this
Good.
goes.
Very nice. So my last question then is that
Yes.
what is the biological implication of this? Because all these fellows are all having something somewhere, whether it is in this planet or some other planet, in this water or some other water, biofluids or some other fluid. They're all existing.
As a biological chemist, I wish I could tell you that these are biologically relevant, but the potentials we are working in, that's not biologically accessible in this planet, because we are at very cathodic potentials. At that potential, in biology, solvent is water. At that potential, all the water will be hydrogen. So we
Yeah,
do draw
yeah.
a lot of inspiration from biology. For example, the mechanisms that we study These actually started from our investigation of oxygen reduction by iron porphyrids, which are very biological.
Uh,
So I mean, maybe someday in a different lecture, I'll show you how similar the mechanisms are. Oxygen, nitric oxide, carbon dioxide, sulfur dioxide. Very similar mechanisms, just different potentials.
well, I'm so glad that we can do probably at some point in time the so-called substitution of new fuels and all that with iron. And we don't have to go for other elements on the periodic table. That's another sustainability angle that you are addressing. Thank you and
Well,
kudos. Yeah, well, all the very best to you,
I
and
hope you
I'm
too.
sure
Thank
that there
you.
will be questions. Yeah, thank you. Subrato, you take it forward.
Yeah. So, is any question there? I have actually two questions. So from the participant. So here you are
I
saying that.
see. I see. Professor Prasanna is also
Okay.
here.
Okay.
Professor Prasanna
Please go ahead.
is coming from visiting us from
MS University.
MS University, Baroda. So he came this morning and gave a lecture. Yeah, thank you.
Yes, thank you. Yeah, it's a wonderful lecture, Professor Abhishek, and congratulations for your recent medal, I guess, Academy Fellowship.
Thank
Okay,
you.
it's a really nice work. I like this CO2, and where you people ended. I was about to ask in maybe my undergrads. I have studied something called as Bohr effect happens in the blood system to sustain carbonate acidic basic pH. So can you comment on similar aspect here? What you are doing?
Prasanna, it's actually difficult because the Bohr effect that you see on carbon dioxide removal in our body, that happens. What I was telling Professor Pradeep, that happens at potentials where the iron can only be iron two. So you really don't have this CO2 transfer via iron in iron one or iron zero state. So I wish I could tell you that it was fancy and this is Bohr effect, but it's not.
Okay. Okay. I have one more question. When you say
Sure.
ethane formation is very what surprise to see ethane formation. Uh, is there any role of acetonitrile you are using? Whether it is getting reduced?
We don't think so because the acetonitrile is mostly a solvent to ensure that the porphyrin and the reagents and CO2 they get dissolved. But when we do this isotopic leveling of CO2, acetonitrile is normal acetonitrile. We do not see any trace of acetonitrile carbon in any of this. Now, it's difficult to actually change the solvent often if it's not soluble, right? These iron porphyrids. So I don't know. Maybe look at in for example in eco solvent, right? The reactivity we see in homogeneous conditions in organic solvent versus heterogeneous in aqueous, they have similarities. So I don't think the solvent is playing a major role here.
Because acetonitrile will get electrolyzed to ethane or ethane rather than I will say ethylamine, uh, and that can
You mean
have
if
a
it gets
similar
reduced?
molecular weight as your ethane.
But
Yeah, I
he
mean,
has isotope labeling and all that.
yeah.
Yeah,
So both the carbons of ethane are isotope level. So we know
right.
it's coming from CO2.
Very good, very good. Then it's actually very wonderful reaction because getting a carbon is like only plants can do that easily.
I know.
So you
So
are
the
putting a
other
plant in the
side of
lab.
that story is to take it forward. I suppose this idea that hydrogen bonded center and the water concentration is driving all this. That concept, have you patented it?
How do you patent a concept? I don't know, Professor Pradeep. You're the expert.
Yeah, yeah, yeah,
You give
yeah,
me
yeah,
instructions,
yeah.
I'll patent it.
Yeah, yeah, yeah. So this idea that well, you got a product That product is what you are patenting, the process to create that. But that
Right.
process involves hydrogen bonding. Therefore, it's a dependent claim. The claim is to make that product. The dependent claim is that this is possible because of the hydrogen bonding. Therefore, hydrogen bonding is claimed.
I see. I see. I see. Well, now you mentioned we are going to think about that. Suman, take
Ultimately,
note.
this is what people will use it. This is what.
True. True. True.
Yeah. Thank
Thank
you.
you. Thank you.
Good. Thank you. Thank you.
So there is a question from Pranayra in the chat. So I am just reading the question. Love the composition for ethane and propane story. Have you considered making the ligand OCH3 on ligand is cyclopropyl to understand radical versus ionic mechanism of serial coupling system?
So, Pranay, how are you, Pranay? Pranay, I believe he's the same Pranay who did his undergraduate research with me, and then he moved to Michigan to work with Melanie Sanford. I hope it is the same Pranay because the question definitely sounds like him. So, Pranay, the heterolytic mechanism comes from this particular kinetic trace that you see, where we followed the porphyrin spectroscopic signature from this iron 2 methyl on the way to make propane. And what happens is this iron 2 methyl converts to an iron 2. So,
Please
this is
mute.
a
Please mute.
heterolytic bond cleavage.
Prasanna, can you please mute your microphone?
So,
Yeah. Thank you. Thank you. Yeah. Please carry on.
So, this iron 2 methyl cleaves this iron 2 C bond heterolytically, leaving iron 2 and methyl minus, and that we can see in the porphyrin absorption spectrum. This 427 SORA feature for iron 2 porphyrin. And yes, Shumon has done experiments with O methyl. He has done experiments with S methyl, and that's his trick now. With O methyl and S methyl, he can actually increase the yield of ethane all the way to 85-90%. I don't know, Shumon knows. With thioether, S methyl, I think it goes to around 90%. So yes, that's a very good thought. We have done that, and it works. All right, he's
Pranay
the
is the
same
same
person.
person. Yeah.
Yes.
Okay.
Yeah. So so that hydrogen bonding wave the wave number of carbonyl when it is bonding to the hydrogen, so that time it is going to be higher.
No, lower,
Jack,
lower, lower.
but yeah, I also thought it should be lower, but written as higher. Just Jack's to 2025 paper.
No, that was ACS catalysis 2025. This one. This is why we did the FTIR spectroscopy of the hydrogen bonded system. This is the experimental iron 1 CO 1935. In DFT, without hydrogen bonding, the iron 1 CO is 1948. Hydrogen bonded iron 1 CO is 1934. Experimentally, in dry solvent, iron 1 CO is 1951. Hydrogen bonded 1935. So it is lower.
Not this case, sir. So initially that one Jack's 2025 paper, that where nitrogen is connected to methyl and there is protonation of hydrogen, and that hydrogen is attached to the CO where the wave number, wave frequency is also increasing. So that one.
Oh, you mean the
Yeah,
okay,
yeah,
okay, the methanol case?
yeah, yeah.
Oh, you read that? Yes. So this one you mean? Is this the one you're referring to?
Actually, your slide is static now. I can see only mechanism of CO reduction, but this is the previous slide. Now,
Wait. So hold on. Sorry, I have to share the whole screen. So there we only yes the one that the story of methanol. That's the one you're referring to, right?
yeah, yeah,
Yeah. In that one,
yeah. I was thinking that
the IR spectroscopy we did.
yeah.
Yeah, this one. This one, the IR spectroscopy we did not have 13 level CO.
Yes, here.
Okay.
Yeah.
So that's tentative. The one that we are 100% sure of is the one where we actually labeled the CO with CO13.
Okay.
You see this blue versus red. Blue is 12 carbon CO, this is 13 carbon CO. So we are absolutely confirmed of the assignments. And this is the one I'll refer to when discussing CO frequencies, because we know for sure these are the vibrations. The
Okay.
other one, we did not have 13 CO. So I would not pay too much attention to that one yet,
Okay.
unless we confirm that with the 13 CO uh, sort of characterization.
Yeah. Got it. So for iron 1, it's binded to carbonyl to make the hydrogen bonding with with the adjacent hydrogen. So for that hydrogen bonding, there should be a negative pole of this oxygen, right? For that
Well, not
bonding.
necessarily oxygen.
Yeah. So
We
how
we
you
do not
will
know
explain that? Yeah.
we do not know
Yeah.
where the charge need has to be. You see, these are DFT calculations, right? So I've done enough DFT calculations to know when to trust them and how much we should trust them. No offense, but the point is, if you look at the DFT calculations, it seems like what you say, that the water has to be hydrogen bonded to the oxygen. But the point is, you can imagine coming up with a geometry where the water is somewhere closer to the carbon as well,
Okay.
right? It's a matter of where you start the calculations with
Okay.
and what are the grid sizes of your optimization protocol. Okay, so this is, I won't, I will tell you hydrogen bonding to iron 1 CO weakens frequency by around 15, 16 wave numbers for sure. Does the negative charge have to be on the oxygen or carbon? Well, DFT says oxygen will help and the spectroscopy matches.
Okay.
But unless I do a parallel calculation where I hydrogen bond to the carbon and check with the pyridine, I cannot eliminate the other possibility.
Okay. Okay. Yeah. Yeah. Got it. Thank you. So any other questions? So anyone has any other questions? Otherwise,
Hello,
we are
sir.
going to close. Okay. So please go ahead.
So, Omiyar, really exciting data. So, I just want to understand, like, as you are talking about the hydrogen bonding is stabilizing the intermediates, but this hydrogen bonding can be affected by pH or the temperatures. So, how much stable these intermediates are with respect to the infrared spectroscopic timescale?
Okay, so at the infrared spectroscopy that you see, they are not in aqueous solvents, they're in organic solvents at room temperature. So the pH is out of question here. What matters here is the acidity of the medium, which depends on if you have saturated CO2. When you add water, it forms carbonic acid. So the concentration of water determines how much carbonic acid you have. So don't think of it in terms of pH. Think of an organic solvent with carbonic acid as in terms of acidity. So these are done at low acidity where we can observe this intermediate. If the acidity is high, this will get protonated and the intermediates will go. Okay. So when you say stable, uh, at room temperature, at low H2O concentrations, they're stable. We can observe them, they're fine, no problem. Okay. High temperature, low temperature, I don't know. We have not done it because we don't have an FTIR cell that will allow us to do temperature dependence. But definitely, if you increase the acidity of the medium, this CO intermediates, the iron 0 CO, gets protonated really rapidly and goes away. So if we do the same experiment with a lot of H2 and CO2, like catalytic condition, we will not see any of the CO intermediate. We'll see iron 2 CO, iron 1 CO, and then everything's gone. The moment iron 1 CO is reduced, it gets protonated and methane is formed. Okay.
Okay, sir. Thank you. And one more question, like you are always talking about this intramolecular hydrogen bonding. So, but there will be another orientation that could be possible for intermolecular hydrogen bonding. So, how you are neglecting that possibility here? What's the mechanism?
That's a very good question. It's not neglecting the possibility. Intermolecular versus intramolecular has a huge entropy difference. So when you think of standard bimolecular reaction, two molecules coming together to form some kind of an adduct, that has an entropic hit of around 10 to 12 kilocalorie, just bringing these two things together. But when it is intermolecular, with the pyridine always present, this entropic hit of bringing the water is already taken care of. the pyridine stays attached to the water. And we know that now because what we have done is we have looked at fluorescent zinc porphyrins with this pyridine in the presence of water. And we can actually see the fluorescence quench really fast when the water is present. So we know the water is already present in the active site before anything. So that takes care of the entropic hit of a bimolecular hydrogen bonding. And if you think of 10 to the power 12, 10 to the power 13 in delta G double decker, that's around 15 orders of magnitude in rate, which goes as exponential of delta G double decker. Okay, so that's why we are fairly confident. Intramolecular, something that comes from outside, intermolecular, that's not going to interfere. It's all going to be intramolecular, and we know the water is there from our spectroscopic investigations.
Okay, sir. And last one, you were talking about this hydrogen bonding. So, have you tried to characterize this hydrogen bonding specifically, like not by CO stretching, with by OH stretching, by scanning it far IR zone, like?
So, okay, couple of things here. If you want to look at hydrogen bonding water with water in the medium using IR, it's never going to happen, because your water is going to drown all the signals from anything in that region. Okay. In fact, you will see this, Soham, and it worries me a little bit. A lot of people do this drift, where they actually do this IR spectroscopy in aqueous medium, and they show water OH frequencies change. You just cannot do that. Water has a huge absorption over there. So conventional IR you cannot do. But what we can do are experiments like 2D IR that looks between the exchange of energy between this NH and OH. Okay, that's something we are doing with Sayan Bakshi in NCL Pune now. He got the samples from Suman and Somili. But apart from that, what we have shown is if you take zinc porphyrin, which is fluorescent, and you take this pyridine, well, porphyrin, this Somili, she has done this. In case of no water, this fluorescent lifetime is there. But whenever you add water, the fluorescent lifetime really quenches fast. And that indicates that this pyridine brings the water close to this porphyrin that quenches the excited state. So we have that evidence that it's there, apart from the CO stretching frequency. And of course, reactivity is there. So.
Thank you, sir. Thank you for the clarification.
Well, if you don't have other questions, I want to congratulate the students who are doing this work. It's a lot of pain and careful monitoring, and it's a continuous struggle, and that ultimately gives you one spectrum that you can show. I can imagine the kind of pain involved in all this.
You know it.
Yeah. So thank you all. The other point is it is important to have a portfolio of patents in this space, and so that activity has to happen to build this into utility. And I feel that all of you, I mean, I'm just talking to students, you should ensure that these things get done in addition to getting them published, not only for you, but also for the institution, for the country, for anyone else. So this is also an effort that you have to do. Ultimately, it might give you a salary, even if when you are on a rainy day, you might get something extra. So that's another thing. That's all that I would like to say. Subrito, you have anything more?
No, sir, that's all. So, thank you, sir, again for accepting our kind invitation.
Thank you, Subrata. Thank you, Professor Pradeep. This was really excellent. I really enjoyed the interaction with the students.
Thank you. Very nice.
All right.
Thank you, Prasanna.
Thank you, Prasanna, for your question. Bye-bye.
Thank you very much. All the very best. Thank you. It's always a pleasure to listen to you.
Sir, I have sent you the link. Can you please join, sir?
Yes, I will. Thank you.
Yes, sure.
Thank you.